I'm sure you've seen this a million times. It's Spider-Man swinging through the city, but something's very different this time around. This Spider-Man is not human. It's actually an AI, and this AI started off knowing nothing about its environment. And yet, it went from falling flat on its face to swinging through the air at over 100 kilometers an hour. So how did it accomplish this? And how did it learn how to swing when it had no human assistance? Let's go back to the beginning. The first thing our AI ever sees is a state. The state could be anything. It could be a view, or some numbers, or it could be a picture of a beautiful house. The point is, the AI is given some sort of sensory input about the environment it's in. The AI then takes this state and outputs an action. The AI has a bunch of inputs it can interact with, and the action describes how they should be set. As humans, we do something similar with video game controllers. The actions can be discrete or continuous. Discrete actions are like button presses, while continuous actions are more like joysticks or levers. For the sake of the Spider-Man AI, all of the actions will be continuous. Finally, the action is applied to the environment, which steps forward in time and outputs a value called the reward. The reward is what motivates our AI, and it's given out like a score in a video game. So you get points for doing the right thing, and you lose points for doing the wrong thing. Our AI's job is to figure out how to maximize the reward it gets by picking the right actions. So states, actions, and rewards. This little sequence we have covered describes how a single frame or time step goes for our AI. In the next time step, the environment will change and a new state is produced, leading to a new action and reward. This process will continue on forever, gathering a state, action, and reward for each time step. Eventually, we may reach a terminal state. This ends the cycle. Maybe the AI ran out of time, or succeeded, or decided to go work at Joe's Pizza. The point is, the loop is broken, the total reward we have received is final, and the AI doesn't get to choose any more actions. This closed-off sequence of states, actions, and rewards forms an episode. By arranging the data like this, we can now select any time step and see its future. The reason we do this is so that we can analyze the outcome of our actions more directly. If we isolate a specific time step, it's tempting to judge actions based on the immediate reward. But if we look into the future, we can see that the reward we got was taken away by a huge punishment. To solve this, we can add every future reward together, creating a new number called the return. This improves the judgment of our actions significantly, but there are still some problems. We aren't really considering the value of time. Yes, we are looking into the future, but how far should we look? Is getting $20 now the same as getting $20 in 10 years? Unless you're really patient, or broke, probably not. Time has value to us, and there's a good reason for that. The future will always have some sort of uncertainty to it. This means that any reward received in the future should be worth less, since it might not happen. The uncertainty also increases with time, so our future reward should scale down with how much time has passed. Let's introduce a new term, the discount factor. This is a value between 0 and 1, which represents how fast the rewards will decay over each time step. Typically, this is set somewhere between 0.9 and 0.99. To use this number, we multiply it together with the first future time step. Since the discount factor is less than 1, this causes the reward to shrink slightly. The time step after that is multiplied with the discount factor twice, making it even smaller. Then we do it 3 times for this one, and 4 times for this one, and so on. Finally, we can take our new shrunken rewards and add them together. This creates a new value called the discounted return. Note how this differs from the regular return. The discounted return actually takes time into account, giving us a much more comprehensive view of how good our actions are. Speaking of which, how exactly are these actions being chosen? This is where the AI comes in. Or more specifically, a neural network. Neural networks are like artificial brains, and their main job is to take input, process it, and make a decision. They accomplish this by linking artificial neurons together, allowing information to flow from one side to the other. Neural networks can also learn, which is accomplished by strengthening or weakening connections between its neurons, changing how information flows through it. We'll come back to the learning later. All we're really concerned with at the moment is how to plug this into the environment. Our network can accept one number for each neuron in the first layer, and since our input will be 20 numbers, we will need 20 neurons. The 20 numbers we feed in will be the state. As I mentioned before, this will contain essential information about the environment. Things like the position of Spider-Man, or the direction of his limbs, or the due date on his next assignment. As for the output, whatever the network spits out will become the action. The AI will have full control over both its arms, so for each arm, we will need a yaw and a pitch angle, which gives them a 3D direction to point in. We will also need one additional input for each arm to control the web shooters. All tallied up, that's 6 numbers, so we'll need 6 neurons in the last layer. Yes, there isn't any leg control, which is unfortunate, but we need this to be as simple as possible so the AI can learn properly. In addition to input and output neurons, the network will also need some hidden neurons. Hidden neurons go in the middle of the network, and they're responsible for giving the AI its intelligence. Without them, the neural network may still learn, but it'll be very limited in its capabilities. For the Spiderman AI, 512 hidden neurons should be enough. This may sound like a lot, but that's actually about 10% of the neurons inside a jellyfish, so in reality, this may be the dumbest Spiderman that's ever existed. Nevertheless, it's still a very capable learner, and we're going to take advantage of that now. All of the things we've talked about so far describe the base for a family of algorithms called deep reinforcement learning. Within this family, there is a variety of different methods we can use to get the AI to learn, so we will have to choose one to get the AI learning. For Spiderman, we will use PPO, which stands for Proximal Policy Optimization. Here's a rundown of how that algorithm works. Our AI, which we will now call the actor, will interact with the environment, generating heaps of time steps and episodes. While the actor is running, randomness will be injected into his actions, so the actor still gets to choose, but the randomness ensures that we explore all of our options. Finally, we will have another AI, known as the critic, which judges how good it thinks our actions are. The critic's job is to try and estimate the discounted returns at each time step. So not only does the critic have to figure out how the environment works, it also has to figure out how the actor is going to react to it, which is also an AI. Oh yeah, and it's got the same brain power as the actor. So if you ever thought your job was hard, try being this guy. Once we have enough episodes and time steps, the actor and critic will look at all the data and learn from it. Due to the randomness we added, there will be a variety of different outcomes in each episode. Some of the episodes will be good, and some of them will be bad, much like Game of Thrones. The critic is constantly trying to guess a value that we will find out in the future, so we can train it by calculating that value later and comparing it to the critic's prediction, which will tell us how wrong the critic is. We can then feed all these error values back into the critic, and through a process called backpropagation, it'll become slightly less wrong next time. As for the actor, we can train it by maximizing the critic's estimate. In layman's terms, we're an athlete, and we want to make our coach as happy as possible by consistently doing what they want us to do. The critic is constantly trying to predict the discounted return the actor will get, but it can't predict the randomness we add to the actions. So what it ends up settling on is the average of all the possibilities, or the value with the smallest error compared to the randomized outcomes. This slightly changes what it calculates from the discounted return to something called the value function, which is defined as the discounted return if the AI behaves normally, or without any randomness. We can use the value function as a baseline for performance. It essentially describes how well the actor should perform from a given state. So if the actor manages to surpass it, then the randomness in its actions must have made them better. This also applies the other way. If the actor's performance doesn't reach the baseline, then the randomness in its actions must have made them worse. We can quantify this idea by subtracting the baseline from the discounted return we calculate. This creates a new term called the advantage function. We can use the advantage function as a guideline on how to improve the actor's actions. If the advantage function is positive, then we want to encourage the action associated with it, and if it's negative, then we want to discourage it. For all the time steps we've gathered, we can calculate the advantage function and then multiply it with this fraction, giving us the error values to feed into the actor. This fraction contains the probability the actor selects the action, which is possible because of the added randomness. This part is really confusing, and quite frankly, a little too complicated for this video. If you're still interested, I've included some links in the description. So we feed all these values into the actor, and by using backpropagation again, we can make the actor slightly better at picking the right actions. So our actor and critic are now slightly better. Now what? Well, we throw out all the episodes we gathered and do the whole thing again. In this new training session, the improved actor and critic will produce better episodes, which will lead to new experiences to learn from. We can keep repeating this process over and over again, improving the actor and critic a little each time. Eventually, the actor and critic will reach a point where they excel at their tasks. At this point, the training is complete. We can now throw away our critic, and our fully trained actor will now dominate the task we gave it. There's only one flaw with this process. Unfortunately, neural networks are prone to forgetting the things they've learned, which could lead to a disaster similar to Peter Parker's performance issues in Spider-Man 2. To fix this issue, PPO adds an extra step to the learning of the actor. Whenever the actor does a training session, we check how different its behaviour has become from its old self. If the current AI has strayed too far away from its old self, then we clamp it, effectively preventing it from changing any more in that direction. This simple step helps the actor retain knowledge he gathered from previous training sessions, which prevents performance drops and allows the new training sessions to be more effective. And for PPO, that's actually all there is to it. Now, let's see what this AI can do. Maybe we'll just stick to swinging. The AI spent a total of 11 hours training, eventually being able to average about 1.2 kilometers per swing. At the beginning, the AI makes no progress at all. Webs are spun randomly, and there's no rhyme or reason to its actions. It just keeps hitting the ground over and over again. After a few training sessions, the AI learns that spinning webs forward is a great way to start. Unfortunately, there is rarely any follow-up, but it's still better than nothing. About half an hour later, it started to learn that shooting more than 2 webs allows it to go a bit further. It started making decent progress, but it was still very sloppy. One of the keys to swinging like Spider-Man is consistency. One bad web can easily nullify several good ones. We can also see the emergence of what I like to call inchworm desperado. Occasionally, the AI gets stuck on the wall and decides to sacrifice speed for survival, leading to this hilariously slow movement. The AI's progress after that began to slow. Most of the learning that took place after this was mainly for the sake of consistency. The remaining training hours were less about exploring and more about fine-tuning. This AI was one of my personal favourites. It now opts for a backflip at the start for extra flair, and really loves this right wall for some reason. I mean, it really loved this wall. We're now 6 hours into training, and we can really see the experience of the AI starting to shine through. It now utilises both of the walls to make the swings more consistent, as well as being a lot faster. There is a newfound sense of calmness to this AI. Overall, it just seems more confident with its actions. And here is the final AI. This one has mastered swinging. It now swings down the middle at very high speeds, occasionally topping 150 kilometers an hour. It's so good in fact, that it doesn't even need to look where it's going, or use its left hand. It has truly fulfilled its destiny. Now, due to some criticism I've gotten on another video, I think I'll just let the AI swing for a little longer. So if you're still here, enjoy.